Hello, my name is Neil Compresto. Today we will be talking about polymer infiltration and pyrolysis PIP. Let's talk about the manufacturing process. First, upstream mining and extraction. Silicon mining. High purity quartz or silica sand is extracted from open pit or underground mines. Carbon sourcing. Coal wood or petroleum coke is mined and processed to serve as a pure carbon reducing agent. This displays the macro and molecular level transformations of raw thermal settings or thermoplastic carbon sources into pure carbon matrices during baking. Carbothermic reduction. The raw silica and carbon are heated together in an electric arc furnace at temperatures exceeding 1900 degrees Celsius to yield elemental metallurgical grade silicon. This demonstrates the phase transformations, microstructural effects, and atomic configurations during this high temperature process. Precursor refining and chemical synthesis. Chlorination. Elemental silicon is reacted with hydrogen chloride gas to form trichlorosilane. These molecular blueprints show how hot chlorine gas attacks a dense metal carbide or silicon carbide crystal lattice, extracting the metalloid elements to yield an amorphous or structured carbon-only framework. Grignard reaction. The chlorosilane undergo chemical synthesis to create polydimethylsilane, a solid precursor polymer. These detailed reaction schematics illustrate the steps of Grignard polycondensation, step growth mechanism, structural variations, and potential side reactions during synthesis. Thermal rearrangement autoclaving. Polydimethylsilane is placed into a high-pressure autoclave at roughly 450 degrees Celsius. This forces the linear silicon-silicon backbone to cross-link into an alternating silicon-carbon skeleton, synthesizing liquid polycarbosilane, the pre-ceramic polymer matrix. This illustrates the chemical structural rearrangement during high-pressure thermal processing. Step 3. Perform component fabrication, fiber spinning, and pyrolysis. Separate silicon-based polymer fibers are spun, cured, and pyrolyzed at high temperatures to create continuous high-strength silicon carbide structural fibers. This diagram details the initial step growth extrusion of raw precameric polymer melt streams into fine filament bundles, followed by low-temperature air vapor cross-linking to build an infusible network shell. 3D fiber weaving. These continuous silicon fibers are woven or braided into multi-directional three-dimensional architectures, shaped roughly like the final desired object. These geometric charts demonstrate how different yarn paths, including orthogonal through the thickness angle interlocks and layer-to-layer angle interlocks intertwine to build fully unified structures. Step 4. Interface surface coating. Conditioning. Chemical vapor deposition. The woven fiber is placed in a gaseous reactor chamber. This diagram details the core transfer sequence within a high-temperature deposition chamber, tracking the mass transfer of precursor gases. Boundary layer diffusion. Surface absorption and film growth. Layer deposition. A microthin layer of boron nitride or pyrolytic carbon is vapor deposited onto the individual surfaces of every fiber. This serves as mechanical fuse to stop structural crack from shattering the component later. This shows how it carries purge unbound molecules between active exposures, establishing an ideal barrier to prevent unwanted powder precipitation. Step 5. Infiltration and pyrolysis. The core PIP cycle. Vacuum evacuation. The coated fiber performed is locked inside a pressure vessel and all air is vacuumed out to eliminate microscopic air pockets. This shows and outlines the exact mechanical and structural setup of vacuum-assisted resin impregnation system tailored to deliver pore-free matrix consolidation during cyclic polymer infiltration and pyrolysis processing. Liquid impregnation. Liquid polycarbosilide polymer is introduced under high pressure, forcing the liquid matrix deep into the tiny voids of the fiber skeleton. This shows a detail of a polymer impregnation system used to consolidate matrices during advanced material synthesis. Low temperature curing. The saturated part is heated to 150 degrees Celsius to 200 degrees Celsius to cross-link the polymer chains, turning into an handleable rigid green body. High temperature pyrolysis. The green body is shifted to an oxygen-free retort furnace under an inert gas, argon or nitrogen blend. The temperature is ramped up to 900 degrees Celsius to 1200 degrees Celsius, causing organic molecules to volatilize as exhaust gases, leaving behind a hard inorganic silicon carbide ceramic matrix. The high-resolution microscopy view show how multiple infiltration cycles gradually seal, porously densify matrix areas, and interface with structural fiber bundles. Step 6. Densification loop. Separation and repeating. Porosity identification. Because the polymer shrinks by up to 30% pyrolysis, the part develops microscopic cracks and voids. It involves mapping distinct defect categories to evaluate matrix densification efficiency. This demonstrates how pore network form across various fiber layouts, material boundaries, and structural matrices. Re-infiltration cycles. The part is extracted from the furnace and placed back into the vacuum chamber to undergo the infiltration, curing, and pyrolysis loop again. The performance graphic illustrates how composite density scales over repeated processing runs, accompanied by standard multi-step processing layout. Multi-cycle completion. This entire loop is repeated 6 to 10 consecutive times until the inner porosity of the composite drops below a strict threshold of 10%. The material data plot below illustrates the precise trajectory of a ceramic matrix composite, reaching multi-cycle completion as a polymer infiltration and pyrolysis sequence repeats over consecutive loops. The physical properties transition from volatile, highly porous state to structural stable ceramic material. Step 7. Finishing and mechanical machining. Diamond tool grinding. Because the polymerized ceramic is incredibly hard, traditional steel or carbide tooling cannot cut it. The near net shape part is refined on highly rigid CNC machine using diamond impregnated grinding wheels over water coolant. The microscopic image isolates the machine surface features of a continuous silicon carbide, fiber reinforced silicon carbide. Precision shaving. The diamond tools remove the final fractions of millimeter to hit precise aerospace tolerance for holes, mating surfaces, and machining hooks. Environmental barrier coating (EPC). In many turbine application, a final protective layer of rare earth silicates is plasma sprayed into the exterior to protect the finished ceramic from high temperature water vapor degradation in flight. Microscopic cross-section illustrates how a multi-layer protective coating bonds to the underlying matrix substrate to stop moisture-induced structural recession. Now we're gonna talk about the product. HPT shroud segments, a highly polished dark gray lock feature, complex structural mounting hooks, curved contours, and integrated fastening channels. It seals the hot gas path by activating as a structural barrier. It forces exploding combustion gases to push the turbine blades rather than escaping over the blade tip. In a jet engine, 18 of these individual shroud segments are linked together to form a static seamless outer ring that sits millimeters away from the spinning tips of the high-pressure turbine blade. High-stage turbine nozzles, airflow-shaped static vanes positioned directly behind the combustor to accelerate direct hot gas flow into the spinning water. Combustor liners, large and walled cylindrical shells that act as inner and outer structural walls of a jet engine combustion chamber and isolates flames exceeding 1,300 degrees Celsius. Hypersonic leading edges, razor-sharp nose cones and wing edges for hypersonic test vehicles which experience intense friction and atmospheric heating. Nuclear fuel cladding, high-density silicon chloride matrix tube used to safely encase uranium fuel pellets inside next-generation fission reaction due to their radiation tolerance and resistance to melting. In conclusion, elemental metallurgical grade silicon is produced by mining high-dirty quartz and processing carbon sources like coal and wood, which are then heated together in an electric arc furnace at temperatures over 1,900 degrees Celsius to trigger carbothermic reduction. Elemental silicon is reacted with hydrogen chloride gas to synthesize trichlorosilane, which is chemically converted into a solid polydimethylsilane polymer. All it undergoes high-pressure autoclaving at 450 degrees Celsius to cross-link its linear backbone into a liquid polycarbonate pre-ceramic matrix. Silicon-based polymer fibers are spun, cured, and high-temperature pyrolyzed to collate continuous high-strength structural silicon carbide fibers. These fibers are then woven into braided, multi-directional, three-dimensional architectures to establish rough shape in final components. The woven fiber performs its place in gaseous reactor chamber with chemical vapor deposition. It's supplied a micro-thin layer of boron nitride or polyethylene carbon as carb vapor deposited onto every individual fiber surface to serve as a mechanical fuse that prevents structural cracks from shattering the component. The coat form is vacuum evacuated in a pressure vessel to eliminate air pockets. Then high-pressure liquid polycarbonate is introduced to deeply impregnate the fiber silicon. The part undergoes low temperature curing 150 degrees Celsius to 200 degrees Celsius to form a rigid green body, followed by inert gas high temperature pyrolysis 900 degrees Celsius 1200 degrees Celsius that volatilizes organic molecules to leave behind a hard inorganic silicon carbide ceramic matrix. Densification pyrolysis causes up to 30% polymer shrinkage, creating microscopic cracks and voids in the ceramic matrix. To fix this part undergoes 6 to 10 consecutive re-infiltration, curing, and pyrolysis loops until its internal porosity drops below a strict 10% threshold. The hardened ceramic component is refined on highly rigid CNC machines using diamond-impregnated grind wheels under water coolant to hit precise aerospace tolerance. Finally, a protective environmental barrier coating (EBC) of rare earth silicates is plasma sprayed onto the exterior to prevent high-temperature water vapor degradation during flight. The Polymer Infiltration and Pyrolysis (PIP) manufacturing process is primarily used to produce silicon carbide jet engine components, such as high-pressure turbine shroud segments that seal the hot gas path to elite commercial aircraft, as well as combustor liners, turbine nozzles, hypersonic edges, and nuclear fuel cladding. This concludes our presentation. Thanks for watching.